So this second talk is titled FL-EVCS, which is going to be about federated learning-based anomaly detection for EV charging ecosystems. I think this is a very relevant topic. EV charging and knowing how to do with FL, something that I didn't see coming, but I'm really excited to learn more about it.
Okay.
So the floor is yours. Please go ahead.
Thank you so much, everyone. Good morning, good afternoon, good evening from wherever part of the world you are attending this session today. So today I'll be presenting our work on FL-EVCS, the Federated Learning-Based Anomaly Detection for EV Charging Ecosystem. So just before diving into this presentation, I just want to quote something out. As our friendly neighborhood superhero once said that with great powers come great responsibility. So I think this wisdom perfectly applies to the realm of EV charging station cybersecurity going forward for sure. So just quickly giving a introduction about me and my major professor. So I'm Shorprit. I'm a PhD candidate in electrical and computer engineering at Iowa State University. My major focuses on secure and reliable computing, and my research endeavors around the development of cybersecurity solutions, particularly pioneering anomaly and intrusion detection system for various use cases using tools like machine learning, neural networks, federated learning, and game theory. And my professor, Dr. Maniman Govindarasu, is currently a distinguished professor at the electrical and computer engineering at Iowa State University. His research includes basically cybersecurity for smart grids and critical infrastructures, IoT security, and real-time systems. He has authored more than 250 peer research publications, received multiple best paper awards, and given several dozen talks and tutorials on the cyber security training sessions. And the major effort he has put into to build the ISU cybersecurity testbed for the smart grid, and successfully has collaborated with many universities, national laboratories, and industries in their R&D projects as well. So this is the agenda for the presentation today. I'll be giving a brief introduction about the cyber physical systems and the EV charging and why this problem basically needs to be addressed. Then a little bit about the EV charging stations architecture, then some prior related work and what the research objective is, followed by our methodology for the federated learning anomaly detection system, followed by the performance evaluation and summary and future work of our work. So just giving a brief introduction before deep diving into the EV charging station. So what exactly are these like systems? So these are like cyber physical systems. These basically integrate computing, networking, and physical processes. So as you can see on the right-hand side of the slide, some examples include the EV charging stations. Just a second. Yeah. So some examples include the EV charging stations, the smart grids, the DERs, and the autonomous vehicles. And the key characteristics of these cyber physical systems are real-time data processing, decision-making, and sensor interactions with tight computation control integrations. So just giving a quick overview of how the CPS architecture works and what could be the potential attack surfaces could be there. So the introduction of basically the communication network layer, which is there, has created broader attack surfaces in these in these cyber physical system, which can be basically exploited by the attacker. And these attack surfaces, as you can see through the orange thunderbolts here, these attack surfaces are increasing every day and can include the sophistication of cyber attacks, making the traditional IT cybersecurity measures very incapable of detecting these attacks. Over the past decades, the cybersecurity issue in the cyber physical system has become very prominent, as depicted through this timeline of the real world cyber attacks on the CPS. So just quickly talking about one or two of those. So in 2019, in a hacking contest, some researchers hacked the Tesla Model 3, basically demonstrating that the serious safety concerns which could be there by gaining control of the vehicle system. And in 2022, very recently, during the Ukraine-Russian war, a group of hackers basically displayed anti-Putin messages on the the charging stations across Russia, impacting the charging of the impacting the charging experiences and highlighting the vulnerabilities which are there in these EV infrastructure. So these basically highlight that the growing number of cyber attacks, especially in EV charging stations, and the plan that it should have to overcome these, and in which cannot be done by the traditional IT security measures in that sense. So there might be a question why basically this talk is about on the EV charging stations, and why there's a need for the focus on the cybersecurity of EV charging stations. So the first would be because of the growing importance of EVCS. So as we can see over the last 10 years, there has been more and more electric vehicles, which basically means a greater need for a reliable and secure charging infrastructure. And because these EV charging stations are essential for shift towards the green energy and the smart grids as well. The unique challenges which these EVCS basically present, these EVCS are highly connected, make to the connectivity over the internet and the Wi-Fi and everything, make them really susceptible to the various cyber attacks which can happen, and they have very specific communication protocols that require the security measures as well. And because the EVs have grown a lot, and the large deployment of EVCS have taken place, so the attack surface has also increased a lot, which makes the job of an attacker or an adversary very easy. So that's why we need to basically focus on the cybersecurity issue. And the main third reason would be because of the privacy concerns and the regulatory compliance which are there, because a lot of raw sensitive data is passed, like the network data which is there, the payment information from your EV charging stations, and some operational data that needs protection. So because of all this, there's there should be a major focus on the cybersecurity of EV charging stations. So talking about how an EV charging station architecture basically looks like. So there are four critical actors in the EV charging station architecture. First would be the EV supply equipment, which is basically the first connection point between the data exchange between your EV and the charging station. And it is done by the protocol named as ISO 15118. It's a very standard protocol used throughout the world. The second actor would be the charging stations. So multiple charging points can ensure basically the compliance of the power limits between the ISO 15118, which is between the EVs and the EV charging stations, and the OCPP, which is between the EV charging stations and the specialized management systems, which take care of mostly the billing and other operational details in that sense. The last one would be the DSO, which basically acts like a global server and basically supervises the electricity distribution and grid stability, and basically integrating data from various charging station management systems for enhancing the efficiency in that manner. So there have been a lot of attacks which have happened on the EV charging stations, which have been exploited by the adversaries. So these are few examples of what the attacks could be, and these are because of the extensive connectivity of the EVCS systems, which I also mentioned in the previous slides, which make them vulnerable to these cyber threats, as adversaries exploit these systems quite a lot. So the main attacks could be which can be faced by the EV charging station ecosystem, could be like the DDoS attacks, which is the distributed denial of system attacks, or the man-in-the-middle attacks, which can happen, or some kind of a data vulnerability or injection attacks, which can happen. So just giving one or two examples about what these attacks basically are. So if we talk about the TCP sync flood attacks, so in an EV charging ecosystem, these basically target the server managing the sessions initiation between the EVs and the charging units in that sense, which can basically how they can basically attack the targeted servers is they can overwhelm the server's capacity to a very high limit, to which after which it can basically result in significant service disruptions, or can prevent the EV charging stations from starting the charging at any given point of time. The second one is OS fingerprinting attack. So I'm not sure like how familiarized the audience is. So I just quickly wanted to give a brief introduction about this as well. So the OS fingerprinting basically allows the adversaries to identify the EVCS devices, operating systems, targeting the known vulnerabilities, and they use techniques like tools like basically Xprobe to map out the vulnerabilities and prepare the targeted attacks. So these are all like some of the attacks which can happen, and the adversary take a lot of time to figure what these vulnerabilities are and how can they bypass it out actually. So if we talk about the related work, just a second. So there has been some research which has been done in the EVCS security for sure, but because since it's a very newer kind of topic in the last 4 or 5 years, it has gained a lot of interest among the researchers. So there has been a few papers published, few contribution given to the EVCS security. But the research gap we figured out was, first of all, yeah, there's a lot more to explore in the EVCS security realm for sure. Then the data privacy issues were not unaddressed, so was not addressed, and the whatever work has been done on the EVCS security as of yet was done on the generic IoT data sets. So basically there needs to be some tailored data sets which were very relevant and specific to some of the EVCS characteristics, if not all, and there should be some privacy preserving solutions which need to be developed to enhance the anomaly detection relevance, effectiveness, and to protect the sensitive raw information which is there among these ecosystems. So the research objective of our work was basically to develop a federated learning based anomaly detection system specifically for the EV charging ecosystem, using decentralized data processing to ensure that we have data privacy and security in that manner, and then to conduct the performance benchmarks against traditional machine learning ADS models to demonstrate that how better the FL effectiveness is there in the real world scenarios or not. And then basically third way was to utilize a EVCS specific data to enhance our model's accuracy in identifying the anomalies rather than using a IoT generic data set. So, but there might be a question that why federated learning is critical for the EV charging ecosystem. Why cannot we just use a machine learning based anomaly detection system that has been used in previous works as well? So, it is basically a five sum of like points which I can state. One is about surely about the data privacy aspect, because it basically ensures that sensitive information basically stays local, protecting the raw data which is there between the EV charging stations, management system, and eventually the DSOs. Then for enhanced security, we can use federated learning because it basically reduces the risk for large scale data breaches by keeping the data decentralized at the at the client level itself. Then resource optimization, basically utilizing the local computational resources itself and reducing the loads on the central server, which could be there because of the aggregation of the entire data. Then the scalability issue, like if we utilize the federated learning concept, it can handle the growing number of EVCS without the central server being overloaded too much. And finally, meeting the regulatory compliances of the data protection regulations, which have been formulated by different organizations in that sense. So this is our FL-EVCS methodology, which we have like formulated for this particular architecture. So as you can see, the EVs are connected to a EV charging station via ISO 15118, and the EV charging stations are eventually connected to a charging station management system via the OCPP protocol. So the charging station management system basically, this architecture basically illustrates the federated learning concept which we have. And like as I pointed out, these EVCS network consists of multiple charging stations and management systems which can be like utilized. So each group of these charging station management system basically represented in a separate cluster, which we can consider as client one, can share data amongst themselves. So basically these charging station management system can share the data with the other charging management system under their own vicinity, which is there in this own cluster under one client within their cluster, so that they can improve their local models in that sense. However, they do not want to share the raw sensitive data which they get from these EVs to the other charging station management system, which are outside their scope, basically. And that's what basically like motivated us, this architecture, to basically utilize the federated learning concept as well. So this federated learning setup basically then like these charging station management system basically train their local model which is there, and can pass the local model parameters which are there, which like the weights and the biases which could be there, to the global server like the DSO, and there the like the federated averaging or some kind of aggregation happens, and then the federated model parameters are again sent back to the charging station management system, and again the whole iterative process basically pans out. So, like, yeah, mostly everyone on this panel might be on this call might be aware of the federated learning process. But yeah, for some of those who are new to this field, just giving an overview of how the federated learning process basically works. So it starts with model initialization. The global model weights are initialized on the server and distributed to the clients in this setup, basically the charging station management system for the initial setup. Then the local training happens, which basically states that the clients pre-processes and train their local global model using the 70% of the data set which we have. Then the parameter sharing happens after training. Basically, the clients send their unique model parameters like the weights and the biases to the server. At the server, basically, once these all the parameters are sent to the server, at the server itself, the aggregation of these updates happen using like in our work, we have utilized the federated averaging algorithm for improving the global model, and eventually the global model again redistributes these federated averaged new parameters back to the clients, and then this process basically repeats over a cycle until and unless the model converges. So for this work, we have basically utilized a dataset named as CIC-EV-SE 2024 dataset. It's a very recently published dataset recording some of the cyber threats in the EV-CS environment with a real EV charger and some Raspberry Pis. So as you can see on the right-hand side, this is the setup of how a local test bed kind of a thing they have set up. They have used different Raspberry Pis and connected them via different protocols which are very relevant to the real EV ecosystem, and then they have basically formulated many attacks so that they can gather this whole information. So in this data set, basically there are 31 CSV files which basically have benign and malicious attacks like the flooding attack, the DOS attacks, and the SQL injection attacks on the interfaces of the EV-SE, which are basically analyzed via the NF stream and the Python scripts. So just quickly, briefly going through what we did after getting the data set. So we performed some pre-processing techniques on the data and the features. So it basically started out with labeling all the records which are there into one CSV file, because initially we had 31 CSV files, so we had to merge them into one CSV file, and then cleansing the data by removing some corrupted records or NaN records. Next, we basically remove the less correlated features which are there, and then converted the categorical variable into the dummy indicator arrays for better use case. And then finally, we use the feature normalization technique followed by SMORT implementation for balancing. SMORT is basically a synthetic minority over sampling technique. It's a very well-known technique which is utilized in the data pre-processing part. So at the bottom right, you can see some of the data set features which are there. So it's a very big data set, almost around like 85 features or something like that. So I'm just like putting out some of the features which are there. So some of the relevant features which you can see would be like the protocol, which kind of protocol is being utilized between this communication, what is the length of the packet which is being sent out, what's the station ID, what's the session ID, what's the information which is actually being like passed out. So these are some of the features which are very relevant to the EVCS and not very generic in the IoT like realm itself. So that's why this data set was is being utilized nowadays for the EVCS anomaly detection purpose for sure. So in our feature extraction process, initially we had like 86 ITOT based features. So by ITOT, I means like information technology. So basically the features which are related to the network and data communication, and OT features meaning the operational technology feature, which are that involve the monitoring and control of physical devices and process in the industrial environments. So because we had like 86 ITOT based features, so we thought that maybe we can reduce some of the features because some of the features might not be highly correlated. So for that, we utilize the dimensionality feature reduction technique. So for our work, we basically utilize two major techniques, which are principal component analysis and information gain technique. So the PCA basically reduces the dimensionality by transforming the features into uncorrelated principal components, and the information gain technique is a very like relevant technique and basically measures the most relevant features by elevating the information gain concerning the target variable which is there. So after performing these two techniques, out of these 86, we eventually got 57 selected features. So as you can see on the right hand side, this is the heat correlation map. So these are the 57 features which were then eventually utilized in our model on the client's localized neural networks as well. So for the model evaluation part, we basically did a baseline ML ADS model check. So for that, we basically collected the raw traffic data, which is directly from the individual charging station management systems, and then all the local trained them on the local DNN model itself without the federated learning concept to have it as a baseline model on a 70-30 trained tested data, and then employ techniques like nearest neighbor, support vector machine, random forest, and just plain neural networks itself. And for our federated learning EVCS model, we basically what I stated in the previous slides as well about the federated learning model, how it basically performs. So for that, but the problem which we faced, one was because we did not have a in raw stream of data coming, rather than we had we had one big CSV file in which all the data was there, and we wanted our all the clients to basically think that every time they run around, it comes out to be a new kind of data. So for that, we basically for each of the charging station management system, which were the clients, so we divided the 70% of the training data into 40 equal parts to fit the federated learning iterative nature, basically allowing for repeated training with not exactly new, but somewhat new subset in each cycle among the 5 clients which we had in our model. And these basically utilize a deep neural network with 4 hidden layers optimized with Adam optimizer and learning rate of 0.01. And then eventually it was tested on 30% of the training data post convergence. And for our model, we basically utilize 2 of the matrices, the accuracy and F1 score. These are very standard matrices which have been utilized in a lot of machine learning anomaly detection systems as well. So I just wanted to emphasize why we basically utilize Flower framework for this and not like some IBM framework or some of the other like relevant frameworks which are there. So the main reason was when I started to basically work in this area. So it was very new to me, and I just started maybe a few months back. I just started to work on this. So it was very new to me, and I wanted to learn a lot as well. So I figured out that Flower basically is something which I can definitely use out because of its compatibility with different ML frameworks like TensorFlow, PyTorch, Keras. That was really relevant for our machine learning algorithms as well. And then it support a lot of customization and extension, that how I can utilize some of the customization aspect, customizing my code in that sense, however I want to frame it out. So that was very essential for my work as a new person working in this federated learning environment. Then it can basically deploy large scale deployments as well. So that is very suitable for a complex environment like a EV charging station, and then it can handle robust communications. And then the other good thing was, like, it's a very growing community, the Flower community, and has a very good contributor base. So as the previous presenter also stated, that he will definitely put that out in Slack channel and everything. So that basically helps the user community as well to learn from it and basically utilize them in your work going forward as well. And there were a lot of extensive documentation and tutorials which were available, which really helped me out to figure out what this federated learning concept is and how I can utilize that out. So that was like a thumbs up and shout out from our end, definitely, to the Flower labs and the community in that sense, for sure. So if I have to talk about the last part of the presentation about the performance evaluation. So for that, our model was trained and tested on system of Intel Core i7-8500 processor and with a 16 GB of RAM. And for our model, we basically utilize Python, skit-learn, and Flower framework, which is support on the back end of the TensorFlow. And for our neural network, basically neural networks layers which are utilized in the client model. So for that, we basically utilize 60, 40, 40, and 20 neurons in the 4 hidden layers which we had, with a ReLU activation function and a sigmoid function for the output layer, because we went for the binary classification as of yet, not the multi-class classification. So as you can see on the right, on the left-hand side, the baseline machine learning model, how it performed on this particular data set. So the best accuracy was achieved for the neural networks, just the simple neural networks. So it was around like 92% with an FN score of almost around 0.923. But for our FL-EVCS model, on the first round, we basically got an accuracy, because the first round can be considered as just the neural networks, because no sharing of data or anything has happened as of yet. So it almost achieved what we achieved in the normal baseline model as well, around 92% on an average across all 5 clients. But when we went to round by round, and the 10th round, where our model basically converged out, so we achieved an accuracy of almost around 97% on an average. So that really, and a very good high F1 score as well as compared to the baseline model. So that basically showcased that how the sharing of the data amongst the various clients helped each client to basically improve their accuracy and F1 score going forward in the training and the testing process. So this basically showcases what the table already shows. So basically, as we can see, the baseline model showcased for the neural networks and the other machine learning algorithms showcased around like 92% on the best. But for the federated learning, on an average, on the 10th round, eventually showcased around like 97%, almost around 97%. And similarly, the F1 score was also like around 97.4 on average. So basically indicating the superior performance which it had and the robustness across all the clients, all the 5 clients which it could perform. So yeah, that was what our work is, and like just giving a summary of what it is. So we wanted to develop a federated learning anomaly detection system using specific EVCS dataset to enhance the anomaly detection system in these ecosystem. We demonstrated high effectiveness of our model with an accuracy of almost around 97% and superior FN scores across all the clients as compared to traditional machine learning ADS models. The future work which we basically want to do is like expand the classification capabilities from right now, because it's just binary with the attack or non-attack. So we want to do it, convert it to a multi-class classification as well, so that it can yield more detailed insights into various types of cyber attack. And we want to explore explore the vertical federated learning aspect as well. And surely now, after the earlier presenter talked about the trace FL thing, that is definitely on my mind, which I definitely want to pursue out and figure out which is the clients which basically like providing the best of the like model parameters and helping out in that sense. So these are some of the references which we utilize in this presentation. And yeah, really appreciate your time. Thank you so much to Flower Labs to giving us this opportunity. And if you have any questions, you can reach out to us. And this work was recently, like last week only, I presented in the ICCC 2024 conference. So it might be like if anyone wants to look at the paper, so it might be available on IEEE Explorer in like a few weeks or so. So yeah.
Very cool. I think thank you very much for the talk. I think it was super interesting. I haven't used myself an EV charging station, so I never even thought that they could be hacked, but makes total sense to build a tool build a framework that can detect when these things happen. So I think we are a bit over time, so I have 3 questions in the meantime. If anyone in the audience has a question, feel free to share it on the chat. Otherwise, I will be the only one asking questions. But please come up with a question. I think there are many interesting things in these slides. So one of the questions I have, which I think you just answered at the end, is that the model is detecting whether something is malicious or not. It's not detecting what type of attack. That will be part of the future work. That's what you.
Yeah. So right now,
good.
basically, it's just like stating out whether, like, because it has been the data set has labels whether what kind of attack it is. Right now, whether it's an attack or not, include the multi-class classification to basically go deep dive into what kind of attacks can happen, and then basically utilizing something like a trace FL to indicate basically trace back to which of these attacks are being transferred from which of the particular clients in that aspect as well. So we definitely want to work under that perspective.
Makes sense. Another question. I have a question kind of related to the data set. So how big is the data set? I presume the data set you were mentioning only contains malicious data, or does it also contain benign, totally?
No, it contains benign and malicious data, like both the data, and like has different kind of like attacks as well in that. But yeah, I'm not sure about the exact like amount of data which is there, because it was a huge data set. All these 31 CSV files which were there, so these were taken at different point of time, and the data was collected at different point of time. So I'm not exactly sure what's the like data length in that sense, but yeah, it's a very big data set, because when we combined it to formulate one big CSV, it took a lot of time first of all, and then the training and the like testing process as well. So yeah.
Yeah, mostly asking because, especially for binary classification, I think a setting like this where you have benign and not benign, you really want to be sure that, because the majority of the time there will be only benign queries, you want to be sure that you have most of them are benign, so you don't have a 50-50 chance.
So that definitely was like something which we considered. So there was not biasness in the data set for sure.
Right.
So it was almost around like 35-40% of the benign data, and the other was like the 35-40% of the attack data, and the other was like the benign data, which is like suitable for any anomaly detection system in that. And so yeah, that was the case which we performed out.
Okay. Another small question, well, 2 connected questions about the data set. So for you, every FL client is one charging station, even though a charging station might have multiple of these terminals. How many clients, how many charging stations did you consider? Like 10, maybe 100, or were all involved in every round, or they were doing partial participation? Can you share a bit of some of the details regarding this, or how you partition the data?
Yeah, sure. So for this work, we basically had 5 clients in which like the clients were basically the charging station management system. And these charging station management systems were connected with the charging stations basically. So for our work, we basically focus on the charging stations individually. There could be multiple charging stations which can be sending the information for. But for this data set, as we see here, there is two charging stations which are basically like contributing to the charging station management system eventually. So, but yeah, we can definitely like when we have a test bed or a setup like this, we can have multiple charging stations basically sending their data to a charging station management system, and then from each of these charging station management system, it will be eventually transferred to the data distributed server operator in that sense.
Okay, cool, interesting. Yeah, maybe you want to take a look at flower datasets because, for example, if you have just a big CSV, you can very easily. I think that's something maybe following what Waris was mentioning at the end. You could very easily kind of like pass it to a partition in flower dataset, and you can partition it into as many as you want, following any kind of mechanism. So that's quite powerful. Maybe you want to take a look for the follow-up work. And then my final question, and I think with this, I don't see other questions, so we'll be ending it, is in the results, you are showing something you're calling the baseline result. Is this baseline result centralized training with all the data, or is only the training of what one charging station on its own with its own data can?
No, with all this 70% data of the entire 100% data set. So that's why we considered it because in our FL model also, when we for all the five clients, we had like in the code, we had set only, and then only 70% of that data set is being utilized in that. But the entire data set is entire 70% of the data set is being utilized for the testing purpose, and then eventually the remaining 30% for the training work.
I mean, I was a bit surprised to see that the baseline that has access to all the training data does worse than FL. I think a very good setup is when both are the same, but usually centralized training, if you implement both, if both have this access to the same amount of data overall, I think centralized training should be able to do.
Should be able to, yeah. That's what we also wanted to figure out, but yeah, eventually the results showcase that. So yeah, that was the thing. But yeah, we will definitely that we had in the mind, but yeah.
Yeah, I mean, maybe it's just a matter of shuffling the data differently or things like that. So
yeah.
But okay, it's cool. Okay, thank you very much.